Hey there. In past videos, we've done some ordinary differential equations and looked at Python solvers that are built into SciPy for dealing with those. For example, the free fall problem where we had a parachutist jumping from a high altitude, and the goal was to basically figure out the position as a function of time, taking into consideration things like drag force and differences in air density. And you'll remember that that was a pretty simple thing. We had a system of ordinary differential equations, the velocity being the derivative of position with respect to time, and the acceleration being the derivative of velocity with respect to time. And even though it was nonlinear, we could deal with it with Python's solvers. But in a lot of real-world engineering type problems, science problems, what you actually end up with is a system of differential equations that are linked or constrained in some way by algebraic equations. For example, in this problem that we're going to look at today, we have a differential equation that gives the voltage across a capacitor as a function of time. But we actually are interested in the total voltage between these 2 points, which is given by an algebraic relationship here. And then we have some further constraints down here. So for example, we're looking at a constant current process, or more interestingly, a constant power process where that constant power is the current times the voltage, but you can't really pull out each individual piece. You have to kind of deal with them as a complete package, or you can't separate them. You have to deal with them all together at once. So these systems, not surprisingly, are called differential algebraic equations, and as I said before, they pop up time and time again in engineering and in science. So today we're going to look at some Python packages for dealing with that, and we may use this as a jumping off point to deal with partial differential equations in Python, but for now we're just going to stick with basic differential algebraic equations. So let's get started. Okay, we're going to need a whole bunch of imports for this one. Obviously NumPy and the plotting library matplotlib. We're also going to do some interpolations, and we're just going to use a cubic spline for this, which we pull in from scipy.interpolate, but you could do a linear interpolation if you really wanted to. Obviously, again, we're going to need the solve IVP problem, and to make our poor man's differential algebraic equation solver, we're eventually going to need fsolve. And then to do the actual integration of the DAE systems, we're going to need a bunch of packages from the Assimulo libraries, which is a Python wrapper around the sundials library that's put out by Lawrence Livermore National Labs. And what that is a whole suite of software written in C and Fortran that does ordinary differential equations, differential algebraic equations, and nonlinear equations, and provides C and Fortran solvers for those. And moving on, what we're going to do is come up with a very simple, simplified model of a battery cell, like a lithium-ion battery. And it's going to be modeled essentially as an ideal voltage source whose actual voltage is a function of what's called depth of discharge, which we'll define in a moment, in series with a resistor. And we're just going to assume that this resistance is constant and does not depend on depth of discharge or temperatures or anything like that. And that is in series with a resistor and capacitor block here. So this capacitor is in series, in parallel with this resistor. And again, we're going to assume the capacitance and this resistance are constant. And the voltage of the cell is given just by the voltage between these 2 points. So if you've taken like an introductory physics class or basic circuits, sometimes they approximate a battery like this, just a internal resistor in series with an ideal voltage source. But this little tweak here just allows you to capture some sort of transient behavior and models that essentially as an exponential change in voltage as a function of time as you charge or discharge this capacitor. And the voltage across that capacitor, which I called V sub C as a function of time, is just given by this. This is just basically freshman physics again. You can just work out these voltages, and that's what you get. So it's a first order differential equation. And what's nice about this is the fact that if current is constant, you can just integrate this and you get the voltage across the capacitor, and then you can just figure out the entire voltage of the battery just by plugging that capacitance voltage into here, and you have the battery voltage as a function of time. And so I want to define this quantity called depth of discharge, which is basically the amount of charge you removed from the cell. So it's a quantity that varies between 0 and 1. 0 meaning a fully charged cell, and 1 meaning you removed all the charge that it has been stored in the cell, and you've taking it out. And that's just equal to the current minus the current times the time. And that's obviously a charge number in coulombs, and then convert it to amp hours. It's divided by 3600. And then we also divide through by the cell capacity to normalize it so that it's always between 0 and 1. And the reason we know that, generally, even though we're assuming these are constants, these resistances and capacitances, they are technically functions of depth of discharge. But in this example, this voltage here, the voltage of the cell, is what's called an open circuit potential sometimes, and that is definitely a function of depth of discharge. So I made up a bunch of kind of fake data here to describe what you often see in a battery, the open circuit voltage, open circuit potential as a function of depth of discharge here. So it's a fully charged cell, it's about 4.2 volts, and as you discharge it kind of goes down, 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 down to the minimum cell voltage, which is typically about 2.5 volts at the full 100% depth of discharge. So this is the voltage we're going to use here for this quantity U, and we're going to use the spline interpolation here to actually interpolate between these values. I just made up something that looks realistic here. These are not actual cell data. They're just something that happens to be kind of similar to what you would actually see in a real cell. So we want to solve this for the voltage. Battery voltage is a function of time given two different constraints. One, that just current is held constant, and the second, that the power, or in other words, the current times the voltage out of the battery is held constant. So as I alluded to earlier, if current is constant, this is a pretty trivial problem. You can just integrate this normally. You just plug in your numbers, and you got your battery voltage. But if the power is being held constant, you have an issue because you cannot disentangle all these different variables easily, and you have to do a lot of jumping through hoops to actually get this to work with an ordinary differential equation solver. And in reality, even if you do, the results are not particularly stable and it's not particularly fast. So there has to be a better way to do that, and that's where we will switch to our differential algebraic equation solver. So for the constant current case, we'll just use the regular solve IVP function from SciPy. And since we've done this several times before, I'm just going to copy and paste the code in rather than doing it in real time, just to save on some time. Okay, off screen I wrote this little class. Let me zoom in a little bit more here. Since we have to pass additional arguments to this integration function, I wrote a class around it so that we can access these variables as member variables of the class. So I've defined a couple of resistance and capacitance values, and again, we're keeping these constant. In reality, these change as a function of both depth of discharge and temperature. Likewise, capacity can change as a function of temperature. So this, we've already done this before, so I'm not going to dwell on it a great deal. We define an initial condition for our integration variable, which is, if you remember up here, we're looking to integrate and get the capacitance voltage. So that's our initial value. We call our ODE solver, and then I just decided to store everything as a class variable, just in case we wanted to access it later, although it seems to be overkill for such a simple thing. And then down here again is just our basic integration function. So let's run that. And down here, let's create a variable called tspan for time span. Tspan is equal to np.lin space. Let's go to from 0 to 3600 seconds, or 1 hour. Let's ask for 100 points. And let's create a variable called, I don't know, let's call it cc for constant current underscore sim. And that'll be equal to our class name, which I believe it was cc ODE for constant current ODE. cc underscore ODE. Let's pass in our time variable tspan and a current of -1. So we'll just discharge at 1 amp for 1 hour. Let's just see if that runs. So far, so good. And let's come down here and just plot the results. So plt.plot cc underscore sim dot t and cc underscore sim dot v, and let's make it a black line. Looks good. This is what we'd expect, basic discharge curve. And the code is fairly straightforward and obvious, and there's nothing wrong with this actually. But let's go on and explore the case where we are not holding the current constant, but instead we are holding the power constant. So the power, whatever we decide it to be, is going to be equal to the current times the voltage, and that's going to be held constant. And let's reproduce this and use the ordinary differential equation solver and solve the problem that way. So I'm going to come down here and basically do the same kind of cut and paste thing just to save time. One issue I noticed here is I had this equation wrong. What I had written was for constant current. So in that case, yes, the depth of discharge is just equal to this term here times the time. But since we're going to have a variable current, we need to write it like this. So I'm going to keep this DOD abbreviation for the depth of discharge, even though this looks kind of funny. So it's a derivative of that with respect to time is equal to this. So we're going to have another differential equation when the current is not constant. So we're going to have this equation here for the voltage across the capacitor, and then this equation here. So now let's go down here and build up this this new class. So let's call this class CP for constant power, ODE. And now we're just going to need I'm just going to reproduce a lot of what we have done before. So I'm just going to paste in here the values of the resistances and the cell capacity. And also let's start the constructor here. So we're going to do the same thing as before, and I need to fix this indentation. Same idea as before, so when we call the constructor, we'll pass in the time and the power that we're keeping constant. Sorry about that street noise, but it's hot here today and I don't feel like running the air conditioner, and they're doing a bit of construction outside. So just as before, I'm going to define our initial conditions. Now remember, we have two differential equations here. We have one for the voltage and one for the depth of discharge, and so that's the zero voltage across the capacitor, and we're starting at a zero depth of discharge. So now actually let's build up that differential equations system. So as before, we're just going to call it equations, and we're going to pass in the time and our variable x, which is our vector of unknowns that we're integrating over. So I like to pull them out here. So let's go v cap is going to be equal to x0, and depth of discharge, DOD, is equal to x1, the first component, or a second component, depending on how you do the indexing. Okay. So our differential equations are essentially the same. So this is the same as above, and this is the one for the depth of discharge. However, the problem is the current is no longer constant in time. So for every t, this value of I is changing. So what we need to do is at every time step solve an algebraic system of equations for these unknowns, I, and probably other things as well. So let's do that. So I'm going to come down here and define a system of algebraic equations, and what we're going to do is use SciPy's fcell function to solve those. So this is what our function definition is going to look like. It's going to take in our unknown variables, and what's nice about this fcell thing, at least in SciPy, is you can pass in additional arguments. So we're going to pass in the capacitor voltage, the time, and the depth of discharge. So let's build this up now. And I always like to define beforehand. I know I didn't do it up in this function here for the differential equation, but I like to define the return value first. It's a kind of a leftover from my C days, and sometimes it can be efficient in allocating memory. So np.zeros, and we're going to return two things. We're going to return the cell voltage and the current. I don't think we need the cell voltage here, but we will need it at a later time. So that's why I'm doing that. And just as before, I want to pull out our, what's going on here? Our, what's going on with the indentation? There we go. Our values, just keep the notation a bit cleaner. So I'm going to pull out the voltage and the current. Now the equation for the voltage is pretty obvious because it's up here. It's all we have to do is basically copy and paste. So where's my voltage equation? Here it is. What else? So that looks good. So let's go on and do res 1. Actually, we're going to need to calculate this open. I'm pointing at the screen here with my finger. Calculate this open circuit potential. So let's do that. That's just copying and pasting from above. And now we can build out the last thing, which is our algebraic constraint. So we have a power, and it's equal to the current times the voltage. So that should be that. Let me just make sure it was P0 that I used defining the class. Where is it? Yeah, self.P0. So that's our constant power. So that's good. So let's just return that residual vector. Return res, and that should define our system of algebraic equations. And now we can go back up here, and in this area here, calculate our voltage and resistances, or not resistance, voltage and current. So this is how we call fsolve. I know I'm just copying and pasting these in, but we've done this before, so should be pretty self-explanatory. Here's our system of equations. Here are our initial guesses, and then the additional arguments that are passed in. And we're just going to pull the current out of that vector, and that is equal to y. I believe it's the first component, right? Yes, first component. So that looks good. We should be essentially, oh no, we need to actually call the differential equation solver from up in our constructor up here. So let's do that now. So our initial conditions, and I noticed the indentations are wrong here, aren't they? We'll take care of that in a bit. So let's put in here, this is our call to the differential equation solver. We're just storing it in a class variable just because. And then we're also pulling out the time, the voltage, and depth of discharge, and also storing those in class variables. Now let's go back. I'm going to shut off the recording and fix these indentation levels. Okay, let us actually just see if there are any major issues there. No, apparently not. Let's actually call this class. I know we haven't calculated the cell voltage yet, just the capacitor and depth of discharge, but let's just do some debugging before we actually pull out the cell voltage. I want to actually copy and reproduce that T-span just in case we want to change it at a later date, so that we don't screw up different cells by having different versions of it floating around. So T-span is that. What did I call this class? CP ODE. So let's call this CP underscore sim, and that's going to be equal to CP ODE, and we want to pass in our T-span and our power. So we're going to go minus 3.5 watts, which is going to give a current roughly of 1 amp for this model. Let's just see if there are any errors there. Of course there are. Oh, I shut down this this session, so I have to pull in the all the imports again. Let me just run the whole spreadsheet, or whole notebook. Run all. Okay, so now there's an error. Somehow I got a double equal up here. No module, that should be zeros, not zero. np.zeros. Run. So far so good. Okay, let's see if we can actually calculate the voltage now. So I don't know really of a good way to do this, so what I'm going to do is just loop over all these capacitor voltages and calculate the cell voltage at the same time. So I'm going to create an empty array called self.v, and that's going to be an empty array. I'm going to create a dummy index called I, and that's going to be equal to 0. And now we're just going to loop over all the times in there. So for every t in our solution time set, we are going to call the fsolve routine to get our voltages out. Then we're just going to append those to that variable v, and then we need to increment our index. So I equals I plus 1. Okay, that should be about it. Let's see if we can run it and plot it and see what the results look like. So let's just see. Let's do that. Let's just see if it runs. Apparently it runs. So let's plot it and see what it looks like. So plt.plot, what do I call it? CP sim, CP underscore sim dot t, CP underscore sim dot v, and a black line. Looks reasonable. So now we're going to go do this kind of what I would consider properly with a differential algebraic equation solver, and then compare the two solutions. And hopefully you'll end up seeing that the differential algebraic equation solver is a little bit simpler in its implementation. We don't have to do these fsolve things. We don't have to do these loops. We could just do it all at once. So I actually am going to, because we have a bunch of plots here, just kind of like put in little headers here so I know where I am in the notebook, and then we'll move on to the DAE solver. So I put in these headers here, Assimulo here, and then constant power using the solve IVP and constant current using solve IVP. What I'm going to do is do the constant power with the DAE solver on the recording, and because it's so simple, I'm just going to not record the constant current part and just kind of tack that on as an addendum. So let's call this class CP. We'll use the same convention as before. We'll call it CP DAE for differential algebraic equation. And we need our resistances and capacities. Where are they? Here they are. So let's just copy all these. Come on. Copy, copy. Something is fishy. And it was fishy because I had accidentally changed this cell to a markdown when kind of doing this like little documentation thing here. So copy, paste. Let's fix this indentation. Cool. So let's come down here and build the constructor. Let me scroll down a bit. So we'll have the same type of thing as before. We'll do the self.p0 is equal to p. And what I think I will do is define the equation system first. So just as before, we're going to define the equations. It takes t and x just like it before. It also is going to take xp, which are all the derivatives. So this is where this begins to differ from the regular differential algebraic equations. Not only do we have to pass in the variables here, we have to pass in the derivatives. And this SW thing is a thing particular to Assimulo. It's for switching and event detection, but we're not going to use that. We need it here, and we're going to just pass in a vector of falses just for that. So, as before, this requires a residual vector, and I'm just going to allocate it ahead of time by doing mp.zeros. Oh my god, I can't type zeros. And this is a four-dimensional system now. And let's also define VCAP. We need, what else? We need the voltage, because we're calculating everything at once. We need to calculate the current and the depth of discharge. And this VCAP is the first, we'll just do it as the first variable here. So this is equal to x0. This will be equal to x1. Likewise, x2 and x3. And as before, we need to calculate the open circuit voltage, and then it's just our equations from the top of this sheet. So to save time, I've already done them here. Again, this is different in the structure. This requires all the derivatives on one side as well as the other parts, and this is equal to 0. So this is our residual vector. These are our equations. This is the differential equation for the capacitor. This is our voltage algebraic equation. This relates the current and voltage to the power. And this is just the depth of discharge, the differential equation for that, just rearranged so everything's on the right-hand side. So that's about it. So we could just return res, and that should be good to go. And we need to come up here and build the rest of the things. So we're going to need a vector of initial conditions and initial first derivatives. And that's one difference between ordinary and differential algebraic equations. Not only do you need to provide initial conditions, but the initial values of the first derivatives. And that can be a problem because we don't really know those, but the solver has a way of handling that. So let's just define guesses for our initial conditions. So x0 is the voltage across the capacitor, and I don't know what that is, so I'm just going to set it equal to 0. x1 is equal to the cell voltage, and these should be x0, should they not? x0, x0, 1 is equal to the cell voltage, and again I don't know it, but they're in the 3 to 4 range, so I'm going to say it's 3.5. x0, 2 is equal to the current, and I don't know what it is, so I'm just going to make up a number and say -1. And x0, 3 is the depth of discharge, and I do know that that is equal to 0. Let's forget, before I forget here, let's do that. Cool, now we need to do the same thing for the derivatives. And I don't know what any of these derivatives are, so I'm just going to set them all equal to 0, and I put this allocation thing up here just because I tend to do that. And now the way the solver is called is different than the solve IVP. It needs the initial time, so I'm just going to do t0 is equal to the first element of t-span. That's a useful thing to sometimes do so that you can have different t-spans that will automatically pull in the correct value. And now we come back to this SW here. We need to pass that into the solver. And we don't really care about it, so we're just going to set it to a vector of falses. So here we go. So it needs 4, since our problem is 4-dimensional, we need 4 falses. Now we need to come up with, we need to tell the solver which of these variables are differential and which ones are algebraic. And that's also a vector of booleans, and they typically give it the name algevar, and it says which ones are differential and which ones are algebraic. So true means differential, and the rest mean false obviously means algebraic. So the voltage across the capacitor, cell voltage is algebraic, current is algebraic, and depth of discharge is differential. So now we're ready to actually call the solver or build the solver object. So we call the implicit model from the Assimulo package, and we pass in our differential equation system, our initial values, our initial derivatives, initial time, and our switch vector here. So now we need to actually call the solver and bind the remaining information to it. So we do that by calling a specific solver, and this IDA is from the sundials package and is kind of bound to Assimulo. I'll link to the sundials package below so you can read up about these solvers, but that's the one we want. We're passing in our implicit problem object, and down here we're setting the algebraic variables to our algevar variable. And now we need to tell the solver to calculate these initial conditions. And for this particular problem, sundials has 2 particular methods for doing that. And in this case, again, I'll link to this rather than just verbally describing what's going on, is we need this particular routine to calculate initial values. So that does that for us. And now we're ready to actually call and run the simulation. And that's as easy as calling the simulation function that's bound to this object. So we want to simulate to our final time, which is the last element of t-span, and we're going to ask for 100 points in between. And these are our output variables. And we will bind these to some class variables just so we have easy access to them. So there we go. Maybe I should pull out the voltages just so that we have them just as we did above. So let's go self.v, is that equal to? It should be equal to the first column of x. So x, all rows, first column. So that should be it. No obvious typo, so let's actually see if this runs. So like before, I'm just going to copy and paste in a t-span just in case you want to change different simulations. And let's call the constructor. What's the name of this class? CPDAE. So let's just call it sim, and let's just have it equal to CP underscore DAE. We need to pass in our t-span and our power, and that I believe was minus 3.5 watts. That should be it. Let's run it and see if there are any issues. Of course there are. Oh, I think I didn't call this equation systems, I just called it equation. So where do we bind that? Up here. Get rid of system. Run. Yay! Oh, nope. The solver ran, but obviously I spelled self wrong somewhere, so let's go back up here. Self.v. Run. Looks good. Now let's just plot it out. So I'm going to clean this up, and it might seem overkill for such a simple problem, but as you can see, like I deal with systems of 10 to 15,000 differential equations, and doing this type of thing up here where you have built-in F cells, not only is it slow and doesn't tend to be reliable, it tends to be, it produces unstable results. It just becomes incredibly unwieldy. So this is incredibly useful, actually. So I'm going to clean this up, and it might seem overkill for such a simple problem, but as you can see, like I deal with systems of 10 to 15,000 differential equations, and doing this type of thing up here where you have built-in F cells, not only is it slow and doesn't tend to be reliable, it tends to be, it produces unstable results. It just becomes incredibly unwieldy. So this is incredibly useful, actually. This has gone on way too long, so as I said, I'm going to do the constant current part using Assimulo. I'm not going to actually record that, but I will put it into the worksheet. I also might want to make some changes here before I upload it and clean it up, comment it, and all that wonderful stuff. So yeah, excellent. Cool. Pretty straightforward, but surprisingly useful. As I said multiple times at this point, these things come up again and again. And so I hope some people here can get some use out of that because this is something I wish I had learned about, a long time ago. I first encountered these probably, last decade sometime, late 2000, say 2009, 2010 area. And I wish I had kind of familiarized myself with this type of thing back in the 90s, early 2000s, because I would have saved myself a lot of work on various projects. So hope some people find this useful. Until next time, see ya.